Welcome to Logistic Equations. Logistic equations talk about population growth when population isn't just exponentially growing. It's proportional to the size of the population, but it also depends on the available resources. So if we look at the formula that we've got written down here, this is our rate of change with population is equal to K, which is just a constant of proportionality, so they'll have to tell you that in the problem, or have you figure it out. P is our population at time t, so P is a function of t, which is why we have dp dt. And our maximum population is M, or that's also sometimes called a carrying capacity. And I want to point out the population doesn't just have to be like what we normally think of as population. It can be anything that's that is growing. So it could be like the weight of something or the volume of something. Usually weight or population, though. So here are two formulas that you need to memorize, especially for the AP exam. The first is our population growth. So dp dt, the rate at which population is changing with respect to time, and then the other is the solution for that differential equation. So if I take dp dt and I solve this, separate out the variables and do integrals and everything, then I'm going to end up with this equation down here. And so you don't have to memorize the second equation, but it makes it a lot easier if you do. P is still our population size, M is our carrying capacity or max size, K is still the constant of proportionality, T is time, and then C is our constant of integration. So that's what we'll have to figure out if they give us an initial value. So this is what a logistic curve looks like. This is the logistic curve, and that's the graph of the population with respect to time. Here is the maximum population, or the carrying capacity, so you can see this function asymptotically approaches that carrying capacity. And then our the other important point on here is the point of the inflection point. So the inflection point happens at half of the maximum population, and this also happens to be the maximum population change. So the slope of the tangent line, this is the point where it's the steepest. And that is important for the example that we are about to do in 1 second. Alright, so here's our example. We have a species of frog, and the population is modeled by a logistic function with a relative growth rate of k equals 0.3 per year, and a carrying capacity of 10,000 frogs. This is a 4-part problem, so I'm just going to do 1 part on each slide, so I don't have to squeeze it all in here. But the first thing we have to do is write the differential equation that describes this population. So this is an example of what you might see for a free response. So I start with my general dp dt equals kp times m minus p. And I just fill in what they told me. So they said that k was 0.3. K is usually a decimal from what I've seen. Population size is what it depends on, what the differential equation is depending on, so that just stays p. And then our max population, or our carrying capacity, was 10,000, so that goes here. You can leave it like this, or you could also distribute it so that you've got this equation down here. Either one of those is fine. So we still have the same situation. Frogs, k is 0.3, carrying capacity is 10,000, so the dp dt we just found is right here. So part B, we have to figure out at what population size is the number of frogs increasing the fastest. So it's looking for, basically, the real question is, where does the concavity change, or what is our maximum dp dt? Where is that slope of the tangent line the biggest? So I drew a little logistic curve here so you can kind of see. This is where our inflection point is, right here, which is also when the derivative of p is a maximum, and that happens at 1/2 of the maximum population. So 1/2 of 10,000 is 5,000 frogs. So when we have 5,000 frogs, that's when our population is increasing the fastest. Alright, relevant information at the top still, frogs, same dp dt. And now we need to know what is the maximum growth rate. So I know that the maximum growth rate happens at 5,000 frogs. So that's my population size. And I just plug that into dp dt. So p is 5,000, and everything else stays the same. M is still 10,000, k is still 0.3. And then when I evaluate that, I get 7.5 million frogs per year, which is a lot, but it's an instantaneous growth rate. So I know that my max is only 10,000, so I'm not going to have 7.5 million frogs. It's just that at that particular instant, that's how fast my frogs are increasing. Alright, part D. If 2,500 frogs are initially introduced into the lake, find the equation that represents the population after T years. So this one, I'm finding the equation that represents the population, which means I need P equal. I don't need dP dt anymore. And this is where you have a choice. So you can start with dP dt and solve it like a differentiable equation where you separate the variables and take the integral. Or we already have this memorized, so we can just plug in the things that we know. Our maximum population is 10,000. So plug that in. K is 0.3. T, I don't know because I'm looking for the population after T years. Anyway, so this is my general formula, my general solution for the differential equation. And then they tell me that 2,500 frogs are initially introduced, and you might remember from physics, whenever you see initially, that means that time equals 0 at the beginning. So I plug in 0 for t, and I get this, because I multiply all of this by 0, basically, so I just have e to the 0, which is the same thing as 1, so that cancels out. And then my population, my initial population is 2,500, so there we go. And then we have 10,000 over 1 plus c, so I multiply both sides by 1 plus c, and I know that c can't equal -1, so that's not a problem. So we'll multiply over here, and we get 25 plus 2,500c is equal to 10,000, and then we just use algebra to solve that to see that c is equal to 3. So plugging c equals 3 in here for that c, then I get this particular solution for when we started with 2,500 frogs. So this is my population size at time t. Alright, here's one for you to try. A calf is gaining weight, and it can be modeled by a logistic function with a proportionality constant of 0.5. So proportionality constant is another way to say k. As an adult, the cow will weigh a maximum of 800 pounds. So they told me it's a logistic function, and then they gave me k and my carrying capacity, basically, or my maximum population, if you want to think about it that way. You have to write a logistic function that describes the calf's growth. So that's dP dt. At what weight is the calf growing the fastest? What is the growth rate? And if the calf weighed 50 pounds when it was born, write the equation that shows its weight at time t, where t is in years. So take a minute and pause the video here, and then when you're ready, start the video again, and we'll look at the solution for this. Alright, so here are the solutions for part A and B. A, here's our dP dt, because our k was 0.5 and our max weight was 800. So P stands for the current weight of the cow. In this case, the population isn't a number of things, it's the weight of a cow, which is fine, because they told us it can be modeled logistically, so we can still use this equation. The weight is growing the fastest at 1/2 the population size, so 1/2 the max population size. So really this should be 1/2 of m, not 1/2 of p. Sorry. And this, the maximum population is 800, so half of 800 is 400 pounds. And then when the cow is 400 pounds, that's when it's growing the fastest, so we just plug in 400 to see that we have a maximum growth rate of 80,000 pounds per year. And remember, that's instantaneous. I know that my cow is not going to get to be 80,000 pounds. It's just at that particular moment, if it continued that growth rate for a year, then it would be 80,000 pounds. But it can't because it's limited. It's a logistic curve, not exponential. So when the calf weighs 400 pounds, it will be growing the fastest at a rate of 80,000 pounds per year. And then for part C, I need to come up with a particular solution. So I have my general solution here for my population size at time t, but I still have a c in it, so I need to figure out what c is equal to, and they gave me an initial condition, so I can do that. So at t equals 0, I plug in 0 to the t, which is nice because it gets rid of basically all of this mess, and then I just have 1 plus c on the bottom. So 800 over 1 plus c equals 50, because that was my initial weight for my cow. And then I multiply by 1 plus c on both sides, which gives me this equation, and then subtract 50, so 50c equals 750, and then divide by 50, which gives me c is equal to 15. So this is my particular solution. This is the size, this is the weight of my cow at any time t. And that is the end. Ask if you have questions.